Welcome to today's webinar. The topic today is Model and Design Timber Structures in RFEM 6 and RSTAB 9. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal software company. I will be the moderator today. My colleague Gerhard Rehm will be the presenter, but he can introduce himself.
Yeah, thank you, Andreas, for the introduction and welcome to today's webinar. My name is Gerhard Rehm. I'm responsible for the customer support and for the development for the timber add-ons. And yeah, I'm happy to present you our software today.
Okay, thank you, Gerhard, for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can enter a short question here and I will answer you. In the case there are too many questions during the webinar, we will answer you via email after the webinar. The other way is to watch the entire webinar and email questions to info@dlubal.com. Then I hand over the screen to Gerhard. Just a moment. Okay, Gerhard, it's your turn.
All right, perfect. Thank you, Andreas. So let's see what I plan today and what I want to present. Maybe I go back to website first and want to show you that we already did a webinar on RFEM 6 with a timber add-on. So you can find it here under news and events, webinars. And here you can just set some filter, for example, past in English and according to Eurocode 5. And you will find all timber related webinars, what we did in the past. And this one here is about a 3D structure in RFEM 6. Today, of course, I don't want to do again a 3D structure because there are, of course, a lot of different ways to show or different options to show. And today I present you a really small object actually. But let's go to the agenda today. So we will model a hip rafter for this hip roof or a part of a hip roof. I will not model the whole roof because of the time. But don't get me wrong. I don't want to present you how to design, in this case, two-span beam with a cantilever. Yeah, that's actually not the aim. So the aim is, of course, loading. Yeah, how do we get the loads on this beam? When we talk about the tributary area, so that's maybe not so easy or not so well known about how to get these tributary areas for this kind of beams. And that's one big issue. And of course, we will design the component. So in this case, the hip rafter. And we will spend a bigger focus today on the printout report. So in the last webinars, or actually during the webinars, what we do for the design add-on, steel, concrete, and so on, we do not spend so much time with it today. I want to spend a bigger focus on it. So because this was always asked, let's see. The aim is to get a really small documentation with all necessary inputs. So without creating hundreds of pages, for example. And the reason why I show you the topics 1 through 4 is topic 5, and this is about parameterization, blocks, and scripting, because the aim actually is to give you an environment, or actually you can create an environment where you can use this beam or this kind of beams easily, and you can repeat the input, for example, with the parameterization where you enter just a few values, so the length and so on, the inclination and so on, and to get results really quick. And this is the big aim. Okay, so let's waste time with the presentation. I will directly go to our program, to RFEM 6. I will not mention all changes compared to RFEM 5 because we did this already in our previous webinar. Okay, so I will give them a name. It's hip rafter. And I will activate the add-on timber design. I don't need the load wizard because I will apply the loads manually. Okay, we can select the standards. In this case, I select the Eurocode 0 plus the SLS combinations for timber. And yeah, I'll leave it for the global Eurocode. But of course, you have plenty of national annexes as well. We'll leave it with the global Eurocode. That's actually all for now. And then let's create this hip rafter. All right. All right, so the normal roof should have an inclination of 30 degrees, and yeah, let's create the beam. I use this tool length and direction here, and I select this line length of 10 meters, and I need to change this angle to 120 degrees to get an angle of 30 or to get an inclination of 30 degrees. All right, here we go. So now I need to create a cantilever and the spans in between. So I will divide these lines, I will divide this line here. You see, there is already a shortcut for this option defined. You can define shortcuts here under View, Customize Menu and Toolbars, and here you have to find the correct tool and just apply here the shortcut by double-clicking it. All right, so I hit my shortcut for it, and I will divide it for the cantilever by 0.8 meters with a true length or with a projected length of 0.8 meters. And again, the length of the half length or the half width of the building should be 6 meters. So I will enter 6 meters here. Oops, here we go. Okay, and I will add another purlin, the same as we see here on the screen. So we have a purlin here on the bottom, or a ring beam, for example. And here we will have another purlin or maybe walls. So it depends on the construction, of course. All right, so I will divide the line again at 3.50 meters. All right, so that's it for one roof side. Now I will create this hip rafter. So we choose the same inclination on both roof sides. So in this case, it's easy. There are more options to create this hip rafter, but of course I can show only one. So let's create a copy in a distance of 10 meters. And here I use this option step links, and I can directly add lines in between the nodes. Okay, I will rotate it by 90 degrees or minus 90 degrees around the apex. And I will copy and move these lines in minus 10 meters. And that's it actually. Now I need to, I will use the connect tool, which is over here, and connect all the lines. Okay, I can delete the unnecessary lines and nodes again. Switch off the grid, and now you can directly draw this line, which represents the hip rafter. All right, we will mirror everything around the mirror plane is in YC direction or in YC plane, and the point B is exactly here in the apex. Okay, so we don't need this line and this line and this line, and also not the nodes, so I will delete it out. Okay, so let's define the rafter. So we can use the tool here, create new single member, or we can just select the lines, and I will activate here the member option, and now I can assign a cross section and a material. Okay, let's start with a cross section. In this case, The minimum height of the hip rafter depends on the jack rafters, of course. So let's say the jack rafters have a height of 20 centimeters, and because of the inclination of 30 degrees, so it's 20 divided by cosinus 30 degree. So the minimum height is at least 23 centimeters. So let's start with 24 centimeter height. But of course, this is not a full truth. When you think about some notches like the bird groove cut or the cuts here on top side, there are also different sections here on the bottom, but we will come to this later. First, we start with a simple rectangular beam. All right, so let's start with 100 by 240. And let's assign a material. So in this case, you can use the filter or just enter your material directly here in this search function. And in this case, I can select this material GL24H according to EN 14080. Sorry. All right, so that's it so far. I just hit the OK button. And now I have this beam. I don't want to have the beam also here because it's the same, it's symmetric. So I just added this to the structure to show you what is possible with the loads and so on for later. Okay, then of course we have the beam, we need support. So I create just 2 nodal supports. Of course, I need to rotate the supports by -45 degrees in this example. So I fix support on the bottom and the sliding support here on the top side. Okay, new one. -45 degrees and should be sliding in X direction. All right. So here we go. We have the model. And now we need the loads, and that's the question now: how we get the loads on this hip rafter without modeling each jack rafters here. That's the aim in this example. Of course, I can add the jack rafters, but then I need to take care of the restraints here on the bottom side. Yeah, of course, the full load in this case should go to the hip rafter for the design, and of course, if I apply a fixed support here, maybe there is a restraint, and then the hip rafter will not get the full load. And of course, it's more complicated it's more time consuming to create all these jack rafters and so on. And I want to show you an example today. How does it work without? Okay, let's create a screenshot first, and let's talk about the tributary area for this hip rafter. Okay, so when we think about the classic hand calculation, how we did it in the past, or how we did it, or how we do it, or how we still do it, we have to think about, okay, what is the tributary area? And so let's focus here on this part, on this second span. And of course, I want to have, I will create a copy of this, and I have these two points or nodes here, which is exactly in the middle. So it's just geometrically, we have no continuous effect. So it's just the basic. And how we get it? We get it by dividing it by 50% of the span length. And now we can measure our tributary length by measuring this distance. Okay, depending on the projection plane and so on. But when we are in the projected area, we can use directly this value. And the tributary area in this case is then exactly here, this purple highlighted area. But of course, I don't want to do this always manually by hand, by measuring something, and this should be done automatically in the software. And I will show you how to do this. So the question is only how. Maybe you know about this option, which was also available in RFEM 5, member loads from area load. Maybe we can check this out. So what we need to do, we need to define, of course, a load magnitude per kilonewton per square meters. and we can define a plane, and we can load members. But of course, I don't have members here because of course the whole load should not be covered by the hip rafter. It should be also covered here by the purlins or walls. And yeah, you see it's only possible for members. And yeah, of course I could member here. I could create here a kind of pseudo member to get the distribution the correct one. Yeah, but another disadvantage here with this member load from Area is it's a kind of, or it's actually an isotropic load distribution. So we have not the option to say, okay, the load goes, yeah, the load should be distributed here in global X direction. This is not possible with this option. So in this case, I have a better option. I use here, create a new surface. And here we have a new surface type called load transfer. And what I will do is I create this surface now. All right, so now you see we have this surface. Yeah, maybe I will create directly all others too.
Now, where's Gerhard?
I want to distribute it in Y direction. Andreas, is there something?
Yeah, we lost a little bit. We lost some seconds. We couldn't hear you, but now it seems to be okay.
Oh, sorry. Should I repeat something or just continue?
Maybe the last two sentences for secure. We
okay.
didn't hear something.
Okay, I'm sorry
maybe
for
20
that.
seconds also.
Yeah. Okay. Good. So, thanks for the information. Okay, so we are looking forward to apply the loads here in Y direction. So that's why we check the axis system, and here we have the option to define the load transfer direction. In this case, I want to transfer it in Y direction. So just click OK, and now let's apply a load. So in this case, an area load. And that's a typical surface load and nothing special actually. So let's apply a load of 1.5 kilonewton per square meter, which is really heavy load actually for a roof, but not so uncommon. All right. You see here our area load, nothing special, but of course you can check the load directly on the beam as well by right-clicking the surface, display load transfer separately. Okay, and now you can see how the load is distributed here. You see here, it's constant over the element, but you can change this easily. Just go again to load transfer and switch this to varying. So this will be also the new default setting in the future version. So it should be available, I guess, next week, that this is the default value, not uniform, but varying. All right, that's all. Just click OK and you see, okay, perfect. It is exactly as expected, but of course there is no load here on the purlins or on the walls. Because right now the hip rafter is covering the whole load from the whole surface, which is of course not the truth. But how to apply here the load also on these lines? So when we check the load transfer surface, you see the loaded objects can be members or lines, and that's the big advantage compared to the member loads from area load option. But you see there is no load, but that's clear because there is no stiffness defined on these lines. So either define a member or just define a line support. So let's do this and you will see directly what's going on. So when you apply the load, when you apply the line supports, it's directly changing the load distribution as well for the hip rafter. And this is exactly what we are looking for. And also the distribution on the rafter looks so far, really nice, and as I expect. So we will do the same also on the other surfaces. So I need to define a line support everywhere where we have a stiffness. Okay, and now we can apply the load. It's 1.5 kilonewton. I guess we have it already here. Just add 2 and 3. Yeah, and that's it. So, and the big advantage here is you will get directly the loads here on this wall for the further design, or for example, for the purlin. Yeah, of course, you can delete the line hinge here and apply directly another beam and connect it with a hinge, for example, to consider the purlin. You can consider also a column underneath. That's also possible. Yeah, but of course, for today's presentation, I will just focus on this hip rafter. All right, so we have defined the loads for load case 1, self weight, and we will create another load case. So I will just copy the load case, copy load case, and let's apply a snow load. Okay, I will deactivate, of course, the self weight, and I will define snow here. Action categories should be snow less than 1,000 meters. Okay, that's all. So you see directly, depending on the action category, the load duration is set automatically. We will skip wind loads and so on. It would be too time consuming now, and but it's the same. Yeah, it's actually the same. You apply not a global load. In this case, you apply local loads. That's also possible. All right, then let's go through the load combinatorics. Of course, we have the design situations for ULS and for SLS, and the result of the design situation. Maybe we can select all of them and switch this from second order, from P delta, to first order, means geometrically linear analysis, which is enough in my example. Okay, so let's check the load combination. Of course, we get all relevant load combinations, and the related load duration as well for each load combination. Okay, so far for the load combination, and let's focus actually only on this hip rafter. So I will create a visibility, and I will define some parameters for the design. So we finished with the loading. So now we can focus on the design. So here I have 3 separate members. I could also model this as 1 members and use intermediate nodes. This is also possible, but in this case, I use 3 separate members, and to bring this back to 1 beam, I create a member set. So we name this hip rafter. And we want to overtake the design properties. So I don't want to have the design properties on each single member. I want to see it on the global or on the complete member set. Okay, so let's go to the next tab, design types. So here we define some specific stuff for the design. We have effective lengths. Let's see what's to do here, and let's check it. Okay, so we have to ask us if stability is an issue here in this case. So when we think about buckling around the around the Z-axis, so we have a lot of jack rafters here, and I can definitely say that buckling around Z-axis is not an issue here. Yeah, at least when we have jack rafters every 70, 80 centimeters. So I can deactivate buckling around Z-axis. The same for lateral torsional buckling in this case. There will no lateral torsional buckling occur. So it is not controlling in the design, definitely not. For Y-axis, okay, when you think about the normal forces are really small, I can imagine buckling around Y-axis is also not a big deal, but let's define the parameters for it to show you how does it work. Okay. So in this tab, you see we have this the support types, and we have one support on start and one on the end. This is the default setting. But of course, we have these intermediate nodes. So I will insert this intermediate node. So we have two intermediate nodes, and we have it fixed in C direction, so around Y direction. But of course, here on the cantilever start, I have no support. So, and you can see here, these are my buckling lengths. We have one for the cantilever, we have one for the first span, and another one for the second span, which can be modified, of course. Yeah, for the cantilever, maybe we can set this directly to no buckling, since there will be no compression force in this rafter, in this cantilever. Okay, so that's it so far for the effective lengths for the design. So the next step is about design configurations. Maybe let's have a look inside. Nothing special. Maybe we can neglect some forces, maybe of a result of P delta analysis. We want to ignore, some internal forces. This can be set here, or some additional setting, which I don't want to explain in detail now. The same for the SLS. Here we have our limits defined, L over 300 for characteristic, and so on. Okay, fire is the same, but we don't spend focus on the fire today. Okay, so the next tab is important for serviceability. So as you can see here, we need a reference length for the serviceability. The reference length should be, of course, per span. As you can see here now, we have only one span. So if we would leave this as it is, it would consider the whole length of the beam as reference length. So in this case, it's 10 meter 38 over 300, for example. This is, of course, not the wish behavior. How we can control this? We can control it by using this design supports. So maybe just hit the F1 button, and then the manual is loaded. And you will see here what is actually the function of a design support. And the first function is the definition of the boundary conditions for the design pressure perpendicular to the grain direction, which was implemented in RFEM 6, and the segmentation of the members or set of members for the deflection analysis. Okay, so we need to define design supports to get the segmentation. So in this case, for the member set start, which is here, we don't need a support, but for the second or for the end, we need one. So I created here. And here you can see we can enter a support length and this factor, this KC90 factor for the design check compression perpendicular to the grain. But I must say it was implemented for this typical straight beam solution. When we think about this bird mouse cut in the cantilever, so it is not possible right now to consider this notch. So therefore, we will use the design supports here now only for the serviceability. That's why we set this to direct support, so we have no inputs for that. Okay, so here we go. We will add this design support also on the intermediate nodes. And we check only the deformation in local C direction. And here you can see our segment length. So we have one segment for the cantilever, the next one for this, and the next one for this. And these values are used for determining the reference lengths. Okay, so that's it so far. Just hit the OK button, and we will also see these design supports here. We can directly deactivate this design support since they are not important anymore for me. Types for members, design supports, and maybe member sets is not important for me. All right. Good. That's it actually. Maybe I forgot one thing because of the loads. Of course, I have copied load case 1, means we need to change the load for snow load. Let's apply 2 kilonewton per square meters. And the load direction should be, of course, projected. All right. So when we check the loads, do not wonder why the load is here displayed also for snow on the true length of the beam. This is a kind of specialty in this load transfer surfaces. They can only deal with loads and project it in the true length of the beam. So when we check it separately again, a minute. Here we go. You see the loads are applied. Sorry, the loads are applied in the projected area, but the internal process converted automatically to the true length. So that's, you must imagine, it's a kind of umbrella. So when you flip the umbrella, it gathers all raindrops. It does not matter in which direction. Is it in gravity direction, or is it a kind of mix of gravity and lateral direction? So the loads are always displayed in the true length direction. Okay, but it's converted correctly, of course. Okay, so let's focus on the design. So we have defined all parameters for the design. We will check this one. So we want to check ULS and SLS. I want to design not the members because I have no inputs for the members. So I have to activate this option because I want to design the members via the parent member set. Okay, I will deactivate this. And that's actually all for now. We can directly run the analysis. I'm sorry for that. It takes sometimes a bit. There are some delays because of this GoToTraining or GoToWebinar tool. That's why it sometimes takes longer. Okay, so let's check the result. So when we check the result here, we have a ratio of over 100% here at this cantilever and also here in this span because of serviceability. Yeah, it's directly listed here in this overview. So let's think about here about this 54%. Of course, it's because of the cantilever goes upwards here because the span here is so long. And of course, because of the short cantilever, you get a really high deformation here. But in reality, yeah, you will not check this deformation here on this cantilever. So that's why you have the option here, member sets, to deactivate it. So when you deactivate this option here, then no design check is done for the cantilever. And this is the option what I want to choose here. And also here, because of the first span, the deformation was a bit too high. So maybe I will change this to 120 millimeter. Okay. So let's run the analysis again. Of course, we have changed the cross section. We need to rerun the analysis also for all load cases or in this case load combinations and of course the timber design. All right, perfect. So that's our design. I mean, I don't spend time now to present you the internal forces and so on. I guess that's clear to everyone. Let's have a small look at the design, directly design by member set. And here you can see all designs. You see there are a few zero values from neglectable internal forces or deformation, but you can define here a small filter, show only something which is bigger than 1%, for example. And then you see all design ratios which are done. So we have tension inside the beam. We have, of course, shear, bending. We have bending and tension, bending and compression. We have stability check. So maybe let's check our buckling factor in this case. So yeah, you see the reduction here is not really much. It's from 100% to 86%, sorry, here. But when you compare the compressive strengths, the compression stress compared to the bending stress, so it's so small, nearly you can neglect it. So it's 10, 20, 40 times smaller than the bending stress. Okay, and of course serviceability. You can check it here separately, or you can overlap both ratios. Yeah, that's possible also. Okay, and maybe let's check one design check again. As you can see, we have here our equations. So you can print this also to the printout report afterwards. You can follow each step. You can control or you can compare every value with your hand calculation. And this gives you a big insight in the program. So it's not a kind of black box. Okay, so you can also check here the ratio over the cross section, or you can check the stresses. So for example, normal that means the normal force is also really small. Yeah. Okay. So that's it for the design. I mean, it's nothing special. If you are interested in more details about the design, I recommend you to watch our first webinar. There we spend more time for the results. Okay, so that's it so far for the design. Let's create a printout report. But before we create the printout report, we want to define a few views to create pictures more easy, and therefore we create a new coordinate system, because right now I'm not able to see the full length properly because it's not in XZ or in YZ plane. So that's why we create here a new coordinate system. So first point is here. So the U-axis is defined by this point, and the plane is defined here. We change the coordinates easily. And this one should be in 0 coordinate, okay. And we'll see we have this user-defined coordinate system. And now I'm able to check the view directly in W direction. And that helps me to get the full length. All right. Let's create a few views. So one view should be the geometry, loads, internal forces, design, for example. This helps me afterwards to create pictures easily for the printout report. So for the geometry, of course, I need a dimensioning. So in the current coordinate system, so for this rafter here, second plane, and the offset should be 0.5. For projection in U direction, the first plane, and we define 0.5 meters, and the same for the projection in V direction by 0.5 meter. So that's it. We need to define a slope dimensioning. Okay, so and that's it. That's actually all about the geometry. We can remove the global axis systems. So, and watch only the U and V. The first view should be the geometry. All right, good. Let's switch off numbering of the members and the nodes. Another view. So the second view should be 0.2. It's loading. And the next one should be internal forces. All right, so we check directly here the envelope. So the third view is internal forces. And the last view should be the design ratio for the timber design. Okay, so and now let's check the advantage here of these views. So for example, when you cancel the view and you set this setting here, maybe apply the load here, and you want to go back again to this view, you can just hit this button here and you get directly the same view while you created this view. This helps me afterwards to create, the pictures and so on. Okay, so let's start with the printout report. Okay, let's create a new one. And that's the biggest question, which comes always, what setting should I choose here? Of course, without to see anything, I don't know either. So I just hit the save and show button, and let's check out what the default setting gives us. Okay, so the big advantage in RFEM 6 is you can have the printout report next to the RFEM. So you can work with both windows at the same time. So maybe, let's start to remove something or just to add something. Here you see a model overview. If you don't like it, just right click it, edit it. You will come back to this window here, and you can rotate it. You can define here the window settings. So maybe this should be this size here, and maybe I don't want to see any dimensioning, and just hit OK button, and it will be updated automatically in the printout report. Okay, so let's come to the next page. Is about the content. You can activate it or you can leave it or not. So it depends on you. But let's start here with the settings here. That's why I check both windows at the same time. And then let's edit the setting, because this window depends on RFEM 6 on the table. Okay, so model location, for example, in the base data, you are able to enter the location of the construction. In this example, I want to switch it off. Materials, okay, materials is interesting. Maybe you can activate the properties or not. I mean, everyone who designs a GL24 should know about the characteristics, but of course you can display the properties, but strengths and so on. Sections, of course, I want to see this in the printout report. When we talk about lines, so you see here which line or which nodes are connected with which line, for example. To be honest, I'm not interested in this. The same for members. Which line is related to the member? I'm not interested in. I will deactivate it. The same for the surfaces. In this case, the surfaces are only for the load transfer. I will deactivate this. The same for the special objects. Here, it shows me, okay, when you analyze according to second order analysis, you need to consider the mean value of the stiffness, but I have a linear analysis. I will not show this information. Nodal supports are important, of course. In my example, I activate here this option, rotated via 3 angles, to get also the angle of or the rotation of the supports. Line supports, I don't need this. Type for members, design supports, I'm not interested in this information. Surface supports, I don't have any surface support, so I can leave it or not, but it does not matter. Okay, effective lengths, of course, I want to see what setting and which effective lengths are defined here. That's why I can leave it. Okay, so for load cases, here, let's go down. You see here load case and a few information. Okay, self-weight is considered or not. You can leave this as it is, or you can use this reduced description. This reduces me everything only to one line, which gives me self-weight and if the self-weight is considered and which load duration it has. So let's come to the design situation. So for the design situation, I want to see the same in a reduced description. And of course, I want to see load combinations as well. But, so when we check this, are the load combinations? They were switched off. Okay, that's why I cannot see it. But I want to see the load combinations as well with a reduced description. Okay, static analysis settings, which solver was used and so on, how many iterations and so on and so on. To be honest, in my opinion, for my case or for my example, it's not important. I will deactivate it. The same for the combination wizard. Okay, loads is of course a topic, but I don't want to see any tables. I will do this by pictures because a picture, of course, mostly says more than some tables. I don't need any guide objects, and I don't need any parts list. Here we see the summary. So for each load combination, we see the summary, the sum of load, the maximum deformation, and so on. For me, it's not important. I will deactivate it. I'm interested in the nodal supports, for example. But in this case, I will define it only for a specific loading. So in this case, it should be for self-weight, snow, and the ULS combinations. That's it. And here I want to define some settings because I don't want to see all of these values. So when we go to notes, and yeah, you see the table is really long with a lot of information. I'm just interested in the values, but not in the extreme values here. Okay, so far that's it. Then let's go to the internal forces by section. In this case, I want to see the member internal forces by member sets. Again, for the loading, but of course not for all loading, only for the design situation 1. All right, and I will define also here some settings. I don't want to see these values and this and this and this because this is the envelope. I want to see only the extreme ones. Yeah, this helps me to reduce the table much. All right, okay, that's it so far for RFEM side. Now let's go to the add-on side. So when we check the add-on, yeah, we will see a few settings here. Maybe we can skip one of those, but for the same for the materials, because the materials we have already here in the basic objects, but let's leave it. Ultimate config, we can deactivate. In my opinion, it's not necessary to show, but serviceability config maybe is important to see which limits were used. Okay, we leave this, but fire, we don't have fire, so I will deactivate this directly. Okay, and I'm interested in the design ratio per member set. Okay, and here I will activate as well this design check ratio. I define 1%, and then I get only designs which are higher than 1%. And I'm interested not in all this information about which member, which location, which stress point, and so on. So that's why I deactivate all this directly. Loading, maybe yes. Yeah, and that's it. Design overview, we can deactivate as well. Right, let's hit the save and show button, and let's see. Before we had around, I guess, 20, 25 pages or something. Now it comes down to 6 pages. And when you see here, yeah, the tables were really small and only the important values are listed here. And yeah, this is actually the aim, yeah, to have only a few pages for this rafter and not 20, 30, 40, 50 or more pages. Of course, nobody reads this. Of course, you can reduce pages here as well. So for example, this page or the content can be removed, then you have 4 pages, and maybe you will find a way to reduce it to 3 pages. Yeah, but of course we need pictures. And now let's create these pictures, and that's why I created the views. So I hit this button here, geometry, and now I will print it to the printout report. So here we go. We have this live preview, so you can activate or deactivate it. So when you deactivate it, the input is a bit quicker. So here I use a name geometry, and it should be window filling, and the height should be only 33% of the page. So when you hit the button again, you will get a preview. All right, that's it. I just hit the OK button, and I go to loading and print this picture as well into the printout report. So this is loads, load case 1. And the same for load case 2. All right. Okay, then we talk about internal forces. In this case, I draw a multi. I draw, or I print more pictures in one picture. Actually, it's a picture-in-picture graphic. So therefore, I create a few new windows. In this case, 2. And then let's check it horizontally. So the first one should be the normal force. The second should be the shear force. And the third one should be the bending moment. All right, let's print this picture. And I select here the option more, but of course not with 33%, but with, let's say, 70%. Here we go. And one more picture about the design ratio. Right. So let's switch this back to 33%. That's enough. All right. Okay, then let's go back to the printout report. Now you see 8 pages. We see the pictures. Oh, sorry, I forgot to rename the pictures here. This should be called internal forces and this should be design ratio. But yeah, for now, it's okay. So you see here, we have 8 pages and we have actually a nice clear printout report created with all, in my opinion, all necessary information. So that's it so far for the printout report. Of course, here in this printout report manager, you can create templates, you can save it and you can use it in another file, or you can just open this file again, change the parameters or change the length of the beams and so on. And that brings me to the next topic. It's about this point number or topic number 5, parametrization and scripting. Of course, if you have this part really often, so if you have really often checks for hip rafters or for different kind of beams, of course, I don't want to model everything the same way what I did in the last 50 minutes. So that's why you can use different options. So I prepared everything already here. I have no time to do this in real time. So here we have the structure. It is the same structure, but only with 2 hip rafters modeled, and also the rafters here I have modeled. And this model works with parameters. So when we check it here, I have parameters defined. And each parameter is connected to the node coordinate. So you see here this yellow corner, and when you check the formula, you see, okay, we use these parameters, cantilever plus purlin, to get this coordinate of 4.3 meters. So when we check it here, it's cantilever plus, what was it? Plus purlin is exactly 3.5 plus 0.8. And the big advantage now is I can change the parameters easily. So maybe let's check this printout report first to see the difference between before I change parameters and afterwards. All right, so maybe let's check the geometry. So this is this picture here. It's about the hip rafter and the rafters, the dimensioning and so on. So maybe I can bring this next to this. Here we go. Let's remove this one here and this one. Of course, it's a big advantage if you have a second monitor, because with one monitor, of course, it's really, it's too small. Okay, so let's open the parameters again. So when you finished with all these parameters, you're able to change this. So I may create an extreme example. Let's say 8 meters, and the slope should be 45 degrees. The purlin should be located on 2.5 meter, and the cantilever is, for example, 2 meters. also for dimensions and for the spacing, which is related to this load on the rafter. Okay, and when I hit the OK button, you see the geometry will be changed automatically. Sorry, this was not my aim. This switched automatically the next example. So yeah, here we go. You see the inclination was changed to 45 degrees and the length was changed to 8 meters. Yeah, and now we can simply update our print report. Hit this update button, and we get automatically all information into this printout report without creating a new printout report, without modeling something. It's just about checking the dimension of the hip rafter. If the design ratio is still okay, if not okay, optimize the cross section, and then you can reprint everything again. All right, maybe let's close the printout report and let's come to the next topic. It's about the parametrization as well, but it's about scripting. So unfortunately, I cannot spend so much time now on scripting, but we did a webinar a few weeks ago about scripting. You can find it also here in this webinar page on our website. But what is the big advantage here for the scripting tool? I have prepared a script, so let's delete all of this and run the script. So it's exactly the same what I prepared in the last 50 minutes, but here I can easily define the parameters. For example, again, 8, 45, number of purlins. So I have the option here, to program with JavaScript how many purlins I want to use. For example, only 1 on the bottom side. And when you hit the run button, the script runs, and you will get the geometry with only 1 purlin. If you run the script again, for example, with 2 purlins, you will get an intermediate support here. So this all is possible. Of course, it needs a bit more experience with programming and so on. But if you are interested in, please follow the webinar, what we did, I guess, last or 2 weeks ago about scripting. Okay, so that's it for this example. Of course, you can save blocks. So we have here this block manager. I guess, I'm not sure, I guess it's always, or it's also shown in this scripting webinar, but you can save structures as block and load the blocks as well. That's also possible, but I will skip this part for now. You see here, there are already a few blocks defined, but not for now. Okay, then let's go back to the hip rafter again. As you remember, we have, or maybe I've used my previous example, this one. So as you know, we have defined here a rectangular section for this cross section. Let's check this out. Okay. Of course, we have some cuts here on the top side for this hip rafter. We have some bird's mouth cuts here on the bottom side, and of course we need to consider this in the design. Of course you can calculate on the safe side with the netto section, but that's why we have implemented also these typical timber cross sections. So in this case, you can directly start with this typical hip rafter section. Also for the valley rafter should be available here. And also when it's cut it on both sides, that's also possible. But when we think about connections, so when we think about how to connect the beams to the hip rafter, I mean, where I lived, it's really typical to use this dovetail connectors, for example, because you don't need additional fastener. Of course, you will apply a fully threaded screws. That's clear for uplifting forces, but that's an easier way. But of course, you will create an additional notch here. So another cross-section reduction, which needs to be considered. So the question now is only if we need to consider also this reduction for the stiffness. So for the design side, of course, we need to consider the reduction. Yeah, when you imagine you have this bird's mouth cut here, and also a jack rafter is connected on the same location. Yeah, then that's an extreme example. And in this case, of course, we need to consider the netto cross section. And so maybe let's create one example here quickly. You should have the time for it. Here we will change this to 200, maybe 280, and the width was 120, and this one should be 35 millimeter. Of course, you need to calculate the correct angle and then the correct height of this reduction. Okay, so let's change this. Here we go. So, and now the question comes up, what about the stiffness? Is the stiffness correct by considering without the notches? Yeah, I have prepared another example here. It's a solid structure which shows the influence of this dovetails. So let's switch off the results and see what we have here. Okay, so the first beam here, when we check the X direction, is a notch along the whole length of the beam. Yeah. So the second one is a solid one, a rectangle without any notch. And here on the third one, we have notches in between, but this notch is filled with a material with E90. Yeah. So when we check it, so these materials are here are defined with a E modulus 90 degree to the grain direction. And the same here, but without any parts inside the holes or inside the notches. Okay, so and when we check the deformation to check the stiffness for this example, you can see the first one was the notch along the whole length. It's around 13.6 millimeter. Here we have 11.6, and here you can see that the reduction with the filled section is nearly the same. Yeah, it's closer, of course, to the brutto cross section instead of the netto section. Yeah, so and that's why we can consider in this case the brutto cross section for the stiffness, but of course for the design we need to use the netto cross section. And this is the next topic what I want to show you how to do this. Okay, so the stiffness here is correct, let's say, and let's go to the sections tab for the design. And here you have the option for this hip rafter to use a different section. So in this case, you can switch this and define the new cross section with a reduced section. So for example, when we think about these dovetail connectors here, you can use, for example, this one. Yeah, and here you can just enter everything 280. This was 120. I don't know, let's say 40 just for example. This should be 120 minus 2 times 25 millimeters. It's 70 millimeters, and this should be 16, maybe, I don't know. Okay, so you see now you have this cross section, and this is the cross section which is used for the design for the ULS checks only. Of course, when you think about this on the bottom, maybe better to neglect this part completely. It will not help so much. Yeah, so this is one way how to consider these reductions in this hip rafter, or in general, how to consider reductions in beam elements. For straight or for uniform rectangular sections, there's also the possibility here to define some where is it? Member sets, here we go, to define some local section reductions, but they are based only on rectangular sections, and you can define only a notch along the whole height or width. So that's typical for these notched beams here. That's also possible. Okay, my last example for today before we finish is another one. The load transfer surfaces to show you what is possible. Okay, so let's think about this roof here. We have purlins and we have hip rafter here, another purlin here on this side. And the question is, always how to get the loads on it easily. Is it on the safe side to design the purlin with the whole load from this rafter, for example, or maybe when this building here is taller, then of course maybe this is design giving, because this gives you a nodal load here, or it gives you a nodal load here in the purlin in the center. So that's always hard to get a good approximation. Maybe two load is too uneconomic, especially for the next parts. Maybe there's a column underneath and maybe another beam underneath the column and so on. So maybe the load is then too much, and it would be good to have the real, let's say, the real distribution. Okay, so let's check the loads here. We have created, or I have created one load case, and here you can see there is a free load as well on this surface, on this part. And let's check the distribution on the beams. So we can check this, and maybe better to check only the members. Okay, and now you can see directly the distribution, which looks really good. So we see the reduction here for the purlin here on the apex, here the reduction because of the hip rafter here, and here we see because of this additional free load, we get more loads on it. And the big advantage here, you can see, I have this semi-rigid support considered here for this hip rafter, because the purlin is not supported here, but here. And this is a kind of, let's say, 2.5D solution. And this helps you maybe to determine the loads, and especially when you think about parametrization, you will get the loads quickly, or you will get the designs quickly for this kind of structures. This should give you only an idea what is possible with this load transfer surface, and this maybe helps you in your daily job. Okay, so I guess I considered everything, and that's actually the end of my presentation. If you have any further question afterwards, of course, feel free to send us an email and we will answer all your questions. Okay, then let's go back to Andrea then. Thank you very much for your attention.
Okay, Gerhard, thank you for a nice presentation. We are in time, or no, a little bit over the time, but it's quite okay. Let me show the website again that I can see you where I can find the recording. Just a moment. Gerhard already showed the page, the webinar page under dlubal.com and news and events. You can find our webinars. And then you have to scroll a little bit down. Okay, that's the next webinars. And where is today's webinar? Sorry. Here's it. Okay, then you have to click on it, and in the next days you will find the recording here, presentation slides, and the models here. Okay, if you don't have got the new software generation RFEM 6 and RSTAB 9, you can try it with our free trial version here above. You can click on it and then download the free trial versions of RFEM 6 and RSTAB 9. With all add-ons, also the timber design add-on. And you can try it for 90 days. Okay, that should be all also from my side. I thank Gerhard for this nice presentation. I thank you for attending. Have a rest or a nice rest of the day. Maybe we can see each other in another webinar. Bye-bye.